But yeah, we'll be listening first from Elizabeth. Elizabeth is a research associate here at UTIG, actually. Just started her position, and she did her undergraduate degree in physics, applied physics at Purdue University, and then did her PhD at Georgia Tech. And she worked with Brittany Schmidt and others on planetary icy interiors, and we'll hear from one of those chapters from her today. So we'll first hear from Elizabeth, and then we'll hear from Enze. So yeah, take it away.
Cool. Hi, everybody. Yeah, it's a nice little informal crowd. I will just give a warning that I haven't given this talk since like April, so it's a little rough. That's what's going on there. Just as quickly, who here is familiar with Europa? Just so I can know how much background to do. Like, okay, fun. This is gonna be great. Okay. So, first off, this title slide is kind of, it has an overlay over it, so it's a little extra funky, but this is the surface of Europa, which is a moon of Jupiter. And I'm going to be talking about how oxidants on that surface, this crazy looking pattern that you see, was in the materials on top of it may be getting into the ocean beneath, and trying to quantify that rate of transport. So Europa, it's moon of Jupiter, is what I just said, was initially discovered by Galileo in 1610. And so when he made his telescope, he made this like little series of sketches, and my PhD advisor has one of these as like a tattoo on her wrist. I kind of want to do the same one day, but I don't want to copy her. So if anyone has like a cool idea of how to turn this into a tattoo that's not copying my advisor, would love that. But here's another picture of it, and you can see that it's just this icy covered moon with kind of these weird surface features. Beneath that icy surface, we have an ocean. So it's a global surface ice with a global ocean that, and then beneath that we have a rocky mantle, and the ice and the rock are completely decoupled. So they're not touching. There's a nice thick water layer between that ice and that rocky mantle. And the water plus ice, so that hydrosphere composed of the frozen and liquid portions, is probably about 100 kilometers thick, which is pretty decent. The entire moon itself is about the size of our own moon, about like 1,500 kilometers. So the surface of ice is being just kind of constantly bombarded by radiation, mostly from Jupiter. And those charged particles are coming in, and they're breaking apart the surface ice. And what that's doing is it's actually breaking them down into very highly oxidized components. So you have O2, you have hydrogen peroxide, H2O2, and then the salts that are on there are also getting recombined in that. So you're getting, as these electrons are coming in, they're hitting the surface, the hydrogen's getting released, and you're just left with this highly oxygenated surface, highly oxidized. And the question of whether or not those oxidants get into the ocean has been actually a really important consideration for Europa's habitability. And that's because without this like source of oxidants, the interior ocean is probably chemically dead. And so from a habitability perspective, you want this extra oxidant source so you can create chemical disequilibria, which can be used by to create different geochemical reactions, such as organic synthesis, but also for metabolic processes. And so figuring out if and how much of these surface oxidants are getting into the ocean is a really important consideration for whether or not Europa may or may not be habitable. And there's been a lot of different papers on this. Here's just some of the more prominent ones of different rates of oxidant transport from the surface into the ocean. So they kind of range from, I think the lowest one on there is 10 to the 2 moles per year of oxidants, all the way up to 10 to the 12 moles per year of oxidants. So that's a 10 order range of magnitude, which is huge. And you'll also notice that a lot of them use kind of either very specific processes. So 2 of them use brine advection, where there's brines and the oxidants get trapped in the brines and the brines advect through the ice. One of them uses, the Greenberg one uses ridge growth, which basically they're just saying that the oxidants slowly kind of like go on top of each other, pushing them down into the ocean. That one's kind of a little bit questioned. And then we have the top model by hand et al. They don't say any geological process. They're just like surface age is probably about 60 to 90 million years old. And if we assume that it just gets into the ocean at that time scale, this is how quickly it gets down. But that assumes that it's all efficiently transported from the surface to the ocean. And the main reason we have this like wide range of models is because we don't know what's going on the surface. Quite frankly, we have a mission going to Europa, but we have no idea what is going on here. So it's really, really hard to constrain how the materials on these surfaces are actually getting into the ocean, if they're getting into the ocean at all. And so I wanted to put this up here because I know we have some icy people in the room, and I just kind of wanted to give everybody a moment to just stare at like, what the hell is going on? Like, I don't know if you can see here, but we have like some like marble textures with like pits and domes, and it's fractured, and then you have these like cyclic, you see this like line here that like goes like this and then like that. You have these bands that look like it's getting stretched apart. Just this looks like a brain. I don't know what's going on there. Like, we don't know what's going on here. So this is why we have this like wide range of estimates. We have no idea what the rate of transport might be. Here's some more examples of just like wild surface features. We've got different types of impact craters, more lineae, chaos, just, yeah, crazy stuff. On the right, more of those like cycloid features. So what I'm proposing is that if we want to constrain this, we need to do it in a way that's agnostic to any particular surface process. We want to look at our transport in a way that is flexible and malleable to a lot of different surface processes, try to simplify it as much as possible. We can do that through a box model. And so by simplifying it very simply from just what is the rate of transport from box A to box B, we can start to get a better idea of how it's getting transported into the ocean, especially by breaking it into not just how is it getting from the surface into the ocean, how's it getting from the surface into the deeper ice shell, and then from the deeper ice shell into the ocean. So breaking it out into two different rates instead of one rate. And by coupling those two rates together, we can start to maybe get a better idea of what it might be. So there's a lot going on in this slide. I'll come back to it over and over again. So don't worry if you don't ingest it all at once. So first of all, let's try to get the idea of what the rate of the surface, that's upper layer, into the lower ice shell might be. Thankfully, this has mostly been done already by some of these prior oxidant models. And what we can do is we look at the surface age and how thick that oxidized layer is, and create minimum and maximum estimates. And so we take those minimum and maximum estimates you can see the different types of oxidized species that have been observed on the surface. And we can create efficiency. So we can have 100% efficiency, which is what the hand model did, or we can do a lower efficiency. So I take a 10% efficiency, since that's the percent of the surface that has subsumption. And subsumption is probably the only direct evidence we have for surface to subsurface transport on Europa. And that's where we have these evidence of features where material has just disappeared. And if we look at some of the lines and features on Europa, there's evidence where it's like there's clear shifting and there's material that's just gone. So we know for a fact that that material is being subsumed. Mm-hmm. And so our minimum model is this 10% model where if we assume this is the only process transporting into the interior, then that is our subsumption minimum model. Whereas our maximum model, we assume the entire surface is recycled in. Okay, so going back to our big box model, the next thing we want to consider is what's the rate of transport from the ice shell into the ocean. Thankfully, we can use some clues from Earth, and that basal ice melt is more or less a continuous process. So even when you have periods of net freezing, there's still usually some areas of localized melt. And so if we can constrain what the melt at the surface, at the subsurface is, we can constrain what that ice to ocean transport is. So we may not know how fast things are going from the surface into the ocean, but we have this one process that we can almost guarantee is occurring, even if we don't know what's going on the surface. And so we constrain that by looking at a net melting shell and then a net freezing shell, and then always having a background rate that accounts for just kind of equilibrating processes where you might have localized melt even during a net freezing shell. Going back to our box model, so we have our two rates of downward transport, and we need to couple them together. But we need to, in order to do that, we need to understand how the volumes of the ice shell and the volumes of the ocean are changing with respect to each other. If we assume that the two volumes together are remaining the same, as the ice shell thickens and thins, we can get its volume as well as the ocean's volume. And so to understand the ice shell thickness, I think it's important to understand that Europa's thermal history has not been linear. This is a proposed model of Europa's thermal evolution. So we have, this is an orbital parameter on the top, and then this is the heat production. So this gray line is a proposed thermal, like the heat production within Europa. And you can see that we have this weird wobbly thing going on. And so I'm going to use this model to kind of push the model forward in terms of, we have this high heat period, we have this wobbly high heat period, we have a colder period, and then a colder wobbly period. And so we can use these different regimes to kind of look at possible thermal states. And just kind of pointing out the wobbly periods, because those are going to be interesting moving forward. So that's how we're going to constrain our ice shell thickness, is through that heat production rate, that model. And then we need to do mass conservation. So looking at our two rates together, we can get what the concentration or number of oxidants in the ice shell is. So this is what the results of that are. So the top is covered, but this is the total moles of oxidants accumulated in the ice shell over time using the thermal model I showed you, as well as the box model. And then this is the fraction. So this is what's the percent of the ice shell that is oxidants. And we can track that over that thermal model through time. And so I think what's kind of interesting to note is that while the number of oxidants within the ice shell mostly increases through time, excluding these oscillatory periods, the actual concentration or fraction actually more kind of decreases. And that's because the ice shell is thickening. So the volume of the ice shell is increasing at a faster rate than oxidants are getting in. So the fraction is decreasing while the actual number is increasing. And for reference, modern day is about 4.5 billion years. So that's about here. And which corresponds to 10 to the -8, 10 to the -4 moles of oxidants within the ice shell per mole of water ice. Going back to the box model, you'll get sick of it, I promise. So if we know, so we've constrained how many oxidants we have in our ice shell, but what about the actual ocean? Thankfully, we know how many are getting in, and so we can get an idea of what the total oxidants within the ocean are. So this is the rate of oxidant transport out of the ice shell due to the basal melt alone. And so I think the thing that's of note here is you have these gigantic spikes, and that's during those oscillatory periods when you have net shell thinning. So you have these large melt events where the ice shell is thinning, and that large amount of melt holding oxidants just drops out oxidants. Whereas when the ice shell is net thickening, you really only have a background melt. So it creates this low oxidant input until you have a melt event, and then you can drop your oxidants into the ocean, creating these spikes. And these are the past models of oxidant input. And so what these results show is that by using that oxidant, the ice shell as like an oxidant reservoir, you get this, for most kind of generally cooling periods, you have a much lower rate of oxidant transport into your ocean, with the exception of during these large melt events. And so what that actually means for the ocean composition, by looking at how the concentration of these oxidants accumulates in the ocean over time, during these melt events, the actual concentration within the ocean also increases. And so you have these oxidizing events within the ocean, which could potentially be similar to like the great oxidation event within Earth's ocean, where it is, instead of being caused by an increase in photosynthesis, it's being caused by these gigantic melt events. So that could have a lot of implications for the ocean chemistry. This could result in potentially higher pH ocean fluids. I'm doing some modeling work on that right now. And then overall, the concentrations of these species are lower than most previous models. And so a lot of previous models have talked about sulfate reduction on Europa, but our model inputs for sulfate are much lower. So it would imply that sulfate reduction is less ubiquitous. So yeah, I think I'll leave it at that. Any questions? I know it was kind of a lot, so.
It's a good talk. I have one question. Yeah. Why it is oxidized from the surface, not from the bottom?
Yeah, so it's because, so it's oxidized on the surface because the radiation, if you have the water molecules or the ice on the surface, the radiation from Jupiter comes in, hits the ice, and then it breaks it apart. So you're left with just the O2.
Mm-hmm.
So that's why you have the oxidized surface.
I see.
And then underneath the ice shell, there's just not any natural source of oxidants within like the seafloor. And that's the same on Earth.
Okay.
So yeah.
Thank you.
So you've only modeled the transfer down. Is there any mechanism for the oxidants to be like refrozen into the ice shell? And therefore you also have a reduction in the ocean that way?
Yeah, that's a good question. So I don't model them being frozen into the ice shell. That's mostly, there's a lot of models of like freezing ice, and for like the scales that this is occurring on, like kilometer scales, when the ice freezes, it mostly expels most impurities, unless it's in the form of clathrates. So you could have CO2 clathrates, but like CO2 clathrate modeling, if I remember correctly, I think those would actually sink, compared to, at least with the pressures involved here. So unless you had some sort of buoyant clathrate, they probably wouldn't get refrozen in. And or unless you have very rapid freezing. If you have very rapid freezing, then you could have impurities included.
So in these like mass melting events, does that mean the ice shell is getting thinner? Is it kind of like ice fracturing where things are like moving around and that creates space for things like seep in? Like what's the main melting like dynamic happening here to cause these oxidants to sink in?
Yeah, so I didn't include it, but I probably should have. The ice shell is within this model varies from as thin as like less than 2 to 3 kilometers up to like 70 kilometers. So that's a huge change in ice shell thickness. But what's actually driving the melt is an increase in the heat production due to orbital excitations. So Europa is in kind of this fun orbital dance with Io, Ganymede, and Callisto, which are other Galilean moons. And these thermal models predict that as that kind of resonance, that dance has evolved over time, there have been periods where the tidal excitation has created a lot of excess tidal heating in kind of cyclical manners, which creates that additional heat production. And so you have a thinning ice shell. Yeah.
Sorry. So your model goes into the future and you have these crazy oscillations far into the future. What are they?
Yeah, so these models do like a forward modeling. And they're driven by the same process. So we're really getting into the nitty-gritty details. It's because there's a cold equilibria and a hot equilibria. And so as radiogenic heating decreases and we go through these different orbital oscillations, when you go through the first scenario, it's because you're bypassing the hot equilibria, and so it's trying to maintain that equilibria, and it's fluctuating up and down, up and down, up and down. Eventually, the radiogenic heating decreases enough that it cools out, and then this second one is when you hit that cold equilibria, and then once again, it's trying to maintain it, and it's oscillating up and down, up and down, up and down. Yeah. Hussman and Spahn is the paper, if you're kind of interested in that, 2004. Yeah.
We have a question from Krista.
Yeah.
Is tidal heating in your model primarily located in the ice or in the rocks?
Silicate. It's with this particular model that I'm using is primarily silicate based. There is a model for primarily ice shell tidal heating, but I use this one because it has a larger set of kind of thermal states. The one within the ice shell is a lot more uniform in just kind of what the evolution looks like. And so if I'm just doing side by side, I can say that this isn't the exact thermal history of Europa, but I can say, okay, this is what a high heat production state looks like. This is what a low heat production state looks like. And this is what a wobbly high heat production and a low wobbly heat production state looks like. And so it allows you to see the different dynamical states. So that's why I chose this particular model. It's just because it has a diverse set of thermal states within it.
Discussion hour has been discussed. Let's thank Elizabeth one more time. And switching screens right now. Please stop. Let's exit out of this one. Someone needs to update this PowerPoint. And let's present this one. Okay. I have an introduction for Enze. Let me just pull it up. There. I know a lot about this work, so I'm excited to see what other people think about it as well.
Can you share a screen?
Yeah.
Oh, you're so right. Zoom. You think we'd all have the hang of it by now. But thank you. There we go. Okay. So Enze is a postdoc at UTIG, working with obviously working with Judy Catania, and his interests encompass machine learning applications in earth science and glacier dynamics. This previous project aimed to generate a large amount of glacier terminus data. Go look it up, please. AutoTerm. It's a great resource for all glacier terminus positions in Greenland. And now that we have this large inventory of these glacier terminus positions, Enze is currently focusing on delivering high temporal resolution observations to investigate the controlling factors of glacier seasonality. So with that, take it away.
Okay, thank you all for coming, and thanks for the introduction. And today I'm going to talk about the compound seasonality in all-life glacier dynamics, and we investigate these things by using a dense observations. And to start with, I'd like to share with you, I might need to hide this first.
Yeah.
Okay, great. So to start with, I'd like to introduce you why we care about the seasonal variation, because for one thing, The seasonal variation has been widely observed over the Greenland ice sheet. A lot of glaciers has seasonal velocity, seasonal timeless variation. And by investigating the seasonal variations, we can have more valuable insights on glacier dynamics. And also, more importantly, if we don't include the seasonal variations in the model, some simulations suggest that we might have a bias in the long term of mass change estimation. And previous study, they're limited by the sparse observation. And when they look at the seasonal variations in Greenland, they can only classify the seasonality based on single mechanism for each glacier. So here we have more and more data. We want to use these dense observations to see if there's any room that we can improve. So, oops. All right. Okay. So what we use include 3 data sets: velocity from its life and its near daily temporal solution, and the timeless is from autoterm. It is generated automatically by a deep learning based pipeline. It has 10 timeless position per month. And the elevation data we use is a novel infusion. It's a novel fusion from SF2 and digital global, and it has 4 DMs per year since 2018. And those figures shows each of the data sets. So we can see that the temporal resolution is really high, and we can clearly see the seasonality within this time series. So, and we use this timeless-driven model to combine the elevation and timeless to predict the velocity, to see if we can reproduce the seasonal velocity by using the elevation, by using the timeless variation. So this figure basically illustrates how the timeless-driven model works. So this is a diagram of the glacier. This part is a glacier, and this part is the glacier timeless, and this part is the ocean. So at this glacier time, and there's a force imbalance. This part is because the ice is thicker than water, so there will be a force imbalance. And as glacier timeless move back and forth, so you can see when it retreats, the force will become larger, and that large force imbalance will be propagated into upstream region, influencing the longitudinal stress of the glacier. And that longitudinal stress will further influence the velocity. And that's why this model suggests the frontal changes, when we have the timeless moving back and forth, it can cause the upstream velocity to be changed. All right, so we have 3 objectives within this study. The first one is to reproduce seasonal velocity changes driven by the timeless variation. We want to see which glacier that we can reproduce the seasonal velocities by using this model. And the second one is we want to investigate the influence of seasonal elevation change to see if we include the seasonal elevation data, we have a larger seasonality or smaller seasonality, or it doesn't matter for the seasonality. And the third one is we want to use this high temporal resolution observations to reveal the compound nature of the glacier seasonality. We want to say if it is true, each glacier seasonality is controlled by a single mechanism, or by influenced by multiple mechanisms. So this is our study area, which includes 5 glaciers in central west Greenland. So these colorful lines represent the glacier termini, and these red points is where we get the velocity observation and simulate the velocity seasonality. And for each glacier, we choose multiple flow line, and we do the simulation on each of the flow line and average them together. So here is the results. The top figure shows the timeless variation. going up means glaciers advancing, going down means glaciers retreating. And the bottom figure shows the velocity time series. The black curve shows the velocity observation, and the red curve shows the simulation. Both red and the blue curve shows the simulation, and I will talk about the difference later on. So in this figure, we can see that our simulation match pretty well with the observation. We can successfully reproduce the seasonal velocity from the terminus variation. When the glacier is retreating, it is speeding up. For example, if you look at here, and when the glacier is advancing, it's going up, the speed going down, it's slowing down. So why is that? When the glacier retreats, it will has a thicker upstream ice, and that thicker upstream ice will generate larger frontal force, which will cause larger longitudinal stress, and that large longitudinal stress will cause glacier to speed up. And that's basically why we can reproduce this seasonality by using this simplified terminus river model. And another thing I'd like to mention is the difference between blue and the red curve. The red curve is a simulation that we assume the elevation doesn't change over time. And blue curve is what we have after involving the seasonally varying elevation. And we can see they're pretty much the same, which means the observed seasonal varying elevation has a little influence on the seasonal velocity. And we want to know why is that. And after we observing the seasonal elevation data, we can see that when the elevation changes seasonally, they're pretty much uniform change along the flow line. They just go up and down without changing the shape of the elevation. And so we think because the elevation change uniformly along such a uniform change would have a little impact on the seasonal velocity. And after that, we're looking at this glacier, Rink. This glacier is a little bit different because it is partially floating in the frontal region. So you can see the flow lines are colored differently because the black one is what we consider grounded flow line, and the blue lines are the floating flow line. We can infer that from the elevation profile. You can see when the glacier is grounded, it has a steeper slope, but when the glacier is floating, the surface elevation is basically flat. And also when we do the simulation, we separate the floating and grounded and do the calculation separately. And we find out that when the glacier is grounded, we can reproduce the seasonality pretty well. So this one is observation versus simulation, and this one is also observation versus simulation. It's just that we extract the seasonal signals only. We can see they matches with each other pretty well. But when we look at the floating flow lines, the simulation is much more muted, which means a flat surface will cause the glacier to be insensitive to the terminus variation. So we think for this uniform elevation change and the surface slope change, we think the slope change has a larger impact on the seasonality. And to confirm that, we did some experiments. We artificially modified the surface elevation profile by first moving it up and down vertically, and second, changing the slope of it. So this is the results, simulation results after moving the elevation profile vertically. And we can see the simulation is pretty much the same. It doesn't change the result too much. But when we are changing the slope, we can see that the difference between different simulations are much more stronger. And when we have a steepened surface, the response of the velocity to terminus variation is much stronger. So this one, this orange one is the steepened surface, and this is simulation. So we can see the magnitude of the seasonality is larger than the other two. So this also echo with our results in ring. So if we go back, you can see the grounded flow line has a steeper surface, so the seasonality is much more stronger, and the floating flow line is pretty much flat, and the seasonality is muted in the simulation. All right. So our time-driven model can explain the seasonality pretty well for these three glaciers, Fuji, Cape, and Ring. So we can see that it matches pretty well overall, but it cannot explain everything. There are some subseasonal phenomena that cannot be explained by the time-driven model, because these subseasonal changes is not caused by timeless, it's caused by something else, which bring us to investigate this compound nature of glacier seasonality. We can see that during the melt season, basically each of them, there will be a pulse-like signal. The glacier speed first accelerate first and decelerate later on within the melt season. So therefore, in each year, there will be a two peak, and we call this bimodal velocity time series, because one of them is driven by runoff, and the other, like this one, is driven by timeless. So, well, this bimodal velocity time series becomes a perfect example to show the compound nature of glacier seasonality. And to explain why we have this runoff-driven acceleration, I want to use this simplified figure to explain. So this one, the blue curve shows the velocity, and the shaded yellow region shows the melt season. At the beginning of the melt season, the subglacial drainage system is inefficient, and when we have the melt water input, it will increase the water pressure, and that increased water pressure will enhance the lubrication effect, which will cause the glacier to speed up. But in the middle of the melt season, at some certain point, the subglacial drainage system transfer from inefficient to efficient. So, and then the water being drained away. The water, although we still have the water input, but all the water being drained away, the water pressure decrease. So the glacial velocity also decreases as well. So that's why we have this runoff-driven accelerations. So again, this figure again, this one is a pulse-like runoff-driven acceleration, but this one is a timeless-driven. Another thing we are confident about this timeless-driven acceleration is that it matches with the simulation, and also when the glacier stops to retreat, it stops to accelerate as well. The timing matches perfectly, basically for all the years. So that's why we are pretty confident that the first one is caused by runoff, and the second one is caused by timeless. And another evidence we have is from the velocity profile. The runoff-driven acceleration usually has a uniform profile because the lubrication can extend far inland, but the timeless-driven acceleration will decay quickly when we go upstream. So this too shows the velocity profile for runoff-driven accelerations and timeless-driven acceleration. We can see that in upstream region, the velocity variation is still strong, but in the timeless-driven one, the variation is more or less negligible. And our timeless-driven model can reproduce some glaciers seasonality, but it cannot reproduce two of them. And for example, for this one, this glacier, this speed up in the winter when the glacier is also advancing, which can clearly not be explained by the time-driven model. Something else is driven the glacier seasonality. And for this glacier, we identify this pulse-like signal in the middle of the melt season, similar. So we think it is a runoff-driven acceleration, and beyond that, it has a winter speed up. As I mentioned, this part is what the time-driven model cannot explain. And also because it has two processes control the glacier seasonality, it also shows the glacier seasonal variation is compound. It's not driven by a single mechanism. And similar things happen for this glacier. We have this runoff-driven acceleration and winter speed up. So why we have this winter speed up? Also, the velocity is shown by use this blue curve, and the melt season is a yellow shaded region. The difference is about timing. When the subglacial drainage system transfer from inefficient to efficient. For the runoff-driven one, the transition occurred in the middle of the melt season. But for this winter speed up, the transition occurred at the beginning of the melt season. So in the winter, the system is also efficient, but in addition to the melt water input, we have other source of water. For example, the remaining water from previous summer and the in-glacial water and the subglacial water from undergrounded water. And at the beginning of the melt season, the system transferred from inefficient to efficient, and the glacier velocity decreased immediately. So to conclude, we improved the description of the glacier system behavior. We have time-driven model can explain 3 of them, and the runoff-driven acceleration has been observed for 4 of the glaciers. And upon that, we have 2 glaciers shows the winter speed up. So to conclude, our seasonal velocity can largely be attributed to seasonal timeless variation, and it can be controlled by multiple mechanisms instead of being controlled by one mechanism. And the seasonal velocity is more sensitive to the slope of the surface instead of the uniform changes in the elevation. So I will leave it there and happy to take questions.
Do you elaborate on inefficient versus efficient drainage system? What the difference and what?
So when we have inefficient drainage system, the water can be stored in the subglacial channel, right? It won't be drained away. So that part of the water can enhance the lubrication effect. If the drainage system is efficient, will we have any water able to drain away efficiently? So there won't be any water left.
Then what is controlling this? What's the switch?
That's a good question, and we don't know yet. What controls the glacier to? Because simply we don't know about this.
That's totally fine. Because my intuitive tells me you said during the winter the surface slope will be steeper, or
Based on our observation in Greenland, the observed seasonal elevation does not change the slope. It changes uniformly along the floor. If we look at this figure. Yeah. This one shows the seasonal elevation change.
So the surface slope is pretty much constant, it just universally changes,
Yeah.
lift or drop.
Yeah, that's why when we incorporate the observed seasonal elevation data, it does not change the simulation results too much.
Yeah, so the driving force, I'm talking about basic hydrology, the driving force for that, which is basically surface elevation. The surface slope is constant, okay?
My explanation would be, so in winter, the subglacial drainage system is blocked by, viscous deformation of the ice.
Okay.
It will creep, and such a creep deformation will block the drainage system. So in the meltwater, if we have enough of the meltwater, and the meltwater will push, will channelize the drainage system, and to a certain point, it becomes fully channelized, and water can be effectively drained away. So, the velocity at that timing will decrease.
Do you think sediments can be plugging out the system? Because the Robo paper that you referenced in terms of like, why is it winter time? That like things are like speeding up or like slowing down. It's like the presence of those sediments
Yeah,
impacting the system too.
yeah, definitely. We can look at the sediment plume at the terminus to infer at which time such a transition occurred. Right, if in the middle of the melt system, we observe there is a sediment plume, and we think at this time the subglacial drainage system transfer from inefficient to efficient.
Yeah, and that actually links to the water problem as well. The viscous blocking you talked about actually is a function of the ice, but also the rock. Whether it's soft sediment or hard rock, really.
Yeah.
Plays really how the water travels.
Yeah.
Have you seen that many sediment forms in your images? Or like because of this modeling work, you haven't looked at the images?
No, I didn't look at the images. Well, I look at the images when I try to extract the terminus position.
Okay,
Yeah, I see them.
you should look at them for sediment forms.
Yeah, that's a good suggestion.
Ponds, commons, clearings. Well, thanks y'all for showing up. I appreciate it. Let's think about it.